Micro-CT is like having 3D X-ray vision. Images are captured as individual planes, which are then stacked together to produce a 3D image, all without harming or altering the sample. So how does this work? X-rays are emitted from an X-ray generator, which travel through the sample and are recorded by the detector on the opposite side. To create an image with contrast, the material must interact with the X-rays in certain ways. Firstly, the material must partially absorb some X-ray photons, while allowing others to be transmitted directly to the detector. Secondly, the material must also allow for differential absorption, meaning different materials in the sample must have different X-ray absorbency characteristics. Without this varying degree of absorptivity, a pure sample would yield a solid gray image. Differential absorption depends on material thickness and atomic weight, with lower thickness and lower atomic weight yielding less X-ray absorption. This leads to varying intensities, creating contrast in the image. The specimen is rotated a fraction of a degree between scans until complete rotation is achieved. These image slices are processed and compiled by computational software, creating a 3D rendering of the sample. Images stacked together like how slices of bread create a loaf, or how Pringles create a delicious snack. Little to no sample preparation is necessary, since no coatings are needed and no vacuum is pulled on the sample during imaging. The samples are not damaged during imaging, so you can use micro-CT for material characterization and even on living animals. For imaging animals, the resolution is usually lower, since the scan time is minimized to reduce X-ray exposure. Since you reconstruct the sample in 3D, X-rays interact with the whole sample. For every slice, the interaction volume will be equal to the cross-sectional area times the slice thickness. Slice thickness is controlled by varying the aperture slits in front of the detector. This governs the resolution in the Z direction, so the thinner means higher resolution. Decreasing slice thickness decreases the X-ray flux hitting the detector, so you might not get enough X-rays to get contrast. Increasing the intensity of the incident beam can lead to blurring. Increasing the counting time increases the contrast, but this leads to longer scans. Use micro-CT when you're not interested in the surface of the sample, just the inside. Focused ion beam, or FIB, is another technique to do 3D reconstructions of samples. Micro-CT is a better choice for analyzing larger samples with lesser detail. Micro-CT is non-destructive, while FIB destroys the samples as it is imaged. Micro-CT can be used to image things in 4D, meaning imaging in 3D at various times to see sample evolution, which is useful for imaging dendrites in batteries. Micro-CT is useful for composites to determine volume fractions in pore distributions and biomedical applications. It's used in the food industry to look at things like the distribution of nuts, caramel, and chocolate in a candy bar, or to identify foreign objects in food. Ew! Sadly, there are limitations to X-ray CT. Resolution of a 3D generated model depends on the quality of the voxels, or 3D pixels, which in turn depend on how thin we can make them. Due to this, micron to submicron resolution is difficult. The edges of the sample also have poor resolution because there isn't a lot of material there to deflect the incoming X-rays. Also, features inside of the sample with similar chemical compositions, for example aluminum and silicon, will not be noticeable in the model since their compositions deflect X-rays similarly. Finally, since there are tons of voxels taken per sample and a corresponding 3D model generated from them, a lot of space is needed to process and store every file.